Good afternoon.
Hello, nice to see you. How are you doing?
Nice. Kinda warm today.
Yeah, spring finally is coming. Hello, guys. Nice to see you. Good afternoon.
Good afternoon.
So, last time we discussed four, system of four equations, Maxwell equations, which can describe electromagnetic wave. So today we want to consider some of these equations in our effort to derive and determine speed of electromagnetic wave propagation in free space. And we will show it. Hopefully we will have enough time. We'll see how it goes. We will show that this is this speed which we determine when will coincide with the experimentally measured speed of light. Means that light is also a form of electromagnetic wave. Let me switch to our slides. So we will consider electric and magnetic field vectors in three-dimensional system of coordinates. So let us start with this system of coordinates first. Will be x, z, and y. So some position of this axis x. Let us consider electric field vector and magnetic field vector. So the propagation of electromagnetic wave in this case will happen along axis x. So if we imagine that such electromagnetic waves can be generated at any point of zy plane in the same phase, so they will create some so-called plane wave with plane as a waveform, like wavefront. So wavefront is a geometric system of points which correspond to the same phase of electromagnetic waves. So if we have such configuration that electromagnetic waves are generated in this plane zy, and propagation is along axis x, so the so-called ray is directed along axis x, which is parallel to the propagation of electromagnetic wave. So we have so-called planar wave. If we have a point source of electromagnetic wave, then we have spherical wavefront, and that's also called spherical wave. However, here we deal with this configuration, and obviously we have two vectors, electric field and magnetic field vector. And like first step, what we need to do now, this is consider Faraday's law as part of Maxwell's system of equations. So we can write it here, integral over closed path of scalar product electric field times ds vector is equal to minus dfb over dt. So first derivative of magnetic field flux. Now let us consider a rectangle of some width dx and length L. So we have width dx and length L. For that purpose, we will have another system of coordinates. So to make it convenient to see what's going on, this will be x, z, y. Also, what is necessary to highlight before we proceed, that both electric field and magnetic field vector, they depend on x and time. They are a function of position along axis x and time. However, they do not depend on y or z. So now let us consider some triangular, rectangular. Here will be electric field in some, so we consider electromagnetic wave in some moment, like instant of time. So as it distributed along axis x. So here will be vector E at position x. Here will be vector E at position x plus delta x. So this delta x is the width of the rectangle. And here, this distance will be L, the length. So now we want to calculate first left side of this Faraday's equation to get this integral. And first step, we need to express electric field vector at x plus delta x. So we can write that E at x plus delta, like dx, should be approximately equal to Ex plus first derivative of electric field over position at time constant, means we consider some instant of time, times dx. So that would be considered as Ex plus a partial derivative of electric field over position, because electric field is a function of two variables, independent variables, position x and time t. So we take partial derivative over position x dx. So taking this into account, we now need to calculate this left side of the Faraday's equation. So when we consider the path in the counterclockwise direction, contributions to this integral over closed path, which is our rectangular. Contributions from the bottom and top sides, like this bottom and these top sides, will be negligible because here electric field vector will be parallel to the displacement vector. So we need to consider only two sides. Like electric field vector will be perpendicular to displacement vector. So that's why we need to consider only those sides of the rectangle where electric field is parallel along sides of this rectangle. So these are left and right sides, and we consider path counterclockwise. That's why the left side of Faraday's equation, which is this integral along closed path of electric field times ds vector, will be equal to electric field magnitude at x plus delta x times L, which is the length of this side of rectangle, and minus E x times L. Now taking into account that E at x plus delta x can be expressed as this equation, we can write that it will be equal to L times partial derivative of electric field over position x times dx. So that is the left side of the Faraday's equation. Now we need to focus on the right side. And the right side, we need to deal with the magnetic field flux, first derivative of magnetic field flux. Now, magnetic field flux through this closed path, rectangular closed path, taking into account that magnetic field vector is perpendicular to electric field vector and is oriented along axis z. So that's something like this. This is our magnetic field vector. Magnetic field flux F B is equal to B, magnitude of magnetic field, times L times dx. So we just have a product of magnitude of magnetic field times area of this closed path. Now, assuming constant position x and the fact that dx is much smaller than the wavelength of this electromagnetic wave, we can write that first derivative of magnetic field flux over time will be associated with the change of like rate of changing magnetic field. So that will be L times dx times first derivative of magnetic field over time at x constant at fixed position. So obviously that can be expressed as length times dx times partial derivative of magnetic field over position. So now we have left and right sides of this Faraday's equation considered in the scope of this example. And we can write the following. So left side is L times d e over dx times dx. And left side should be minus this first derivative of magnetic field flux, which is L dx dB over dx. Oh, sorry, not x, but t. It should be time. So from here, since we can cancel these guys, we get the relationship between first partial derivative of electric field along position x and first derivative of magnetic field over time t. So this we keep in mind. We will need this in the future also. And we can also apply our next step will be to consider force Maxwell equation, which also has this integral over closed path, but magnetic field vector times ds vector, which we considered in details last time, and repeat this procedure in a similar way. So now let us draw again a system of coordinates. So it will be x, z, and y. So we will consider now in this plane zx some rectangle. So it will be also width dx and length L. So we remember that here we have magnetic field vector Bx. Here another magnetic field vector Bx plus delta x. We consider them in an instant of time. So time is constant. Now we also need to show our electric field vector. So it will be perpendicular to the plane of this surface defined by closed path along axis y. So this is our electric field vector. So now we recall force equation of this system of Maxwell equations. This is integral along closed path time magnetic field vector, like magnetic field vector times ds vector is equal to mu naught times I plus epsilon naught times mu naught times first derivative of magnetic of electric field flux over time. So now we deal with free space. So that's why electric current can be set to 0. We don't need to worry about it. So now when we look at this plane of zx from top, from the direction of axis y, and go counterclockwise in our integration, then we can also write the following result of this integral in the left side of force Maxwell equation. So here is this integral ds vector. Also, we will have only contributions from left and right side of this rectangle, and top and bottom sides, they will not contribute because of perpendicular orientation with respect to magnetic field vector. So here it will be bx times L minus bx plus delta x times L. And this is approximately equal to minus L times first derivative of partial derivative of magnetic field vector over position times dx. So this is the left side of the force Maxwell equation, and we need to think about the right side, which represented with this term. So magnetic field, electric field flux is equal to electric field magnitude times length of this rectangular and times its width, dx. So first derivative of electric field flux over time will be given as L times dx, first derivative, like partial derivative of electric field over time. So means that if we say here first partial derivative, means that we consider another variable as constant. So and just add here x constant to highlight, but you don't need to show it because it's already shown by partial derivative instead of just derivative. Now we can put these sides, left and right side, together. So this is our left side, this is our right side. We have minus L times delta B over delta x times dx equal to mu naught times epsilon naught L dx, partial derivative of electric field over time. Okay. Now, based on this equation, we can cancel length and width of the rectangle, and we can write that first derivative, a partial derivative of magnetic field over position along axis x will be equal to minus mu naught times epsilon naught times the first derivative of electric field over time, first partial derivative, not forget. So This equation is also important for us. This relationship between space change, like changing, varying in space magnetic field and varying in time electric field. So now let us come back to our previous equation. Call it 1 star. This will be our equation with double star. Now let us write down both of them in order to have them in front of us, because we will need to take some derivatives of these equations. So it will be, let me just write here the first equation so we can see it here. It will be partial derivative of electric field over position equal to minus partial derivative of magnetic field over time. Okay. E over x minus dB over time. So now what we need to do, this is our equation 1 prime. Let us take the derivative of this, our first equation, with respect to position x, and combine it with the derivative of second equation with respect to time. So first we take derivative of first equation with respect to position. So it will be d square electric field over dx square. So it's already second derivative over position equal to minus d over dx dB over dt. So we took partial derivative over position x of left and right side of this first equation. Now let us do a similar procedure. Let us take partial derivative over time of second equation. So it will be d over dt. Here will be dB over dx equal to d over dt of this left side of the second equation. It will be minus mu naught epsilon naught times dE over dt. So what do we see here? We have these and these identical terms in both equations, just with this minus. That's why we can write that, based on these two equations, that second partial derivative of electric field over position should be equal to minus d over dt minus mu naught epsilon naught times first partial derivative of electric field over time, and eventually it will be mu naught times epsilon naught times second derivative of partial derivative of electric field, not over time. So the same manner, we can do one more operation. So this we keep in mind already. In the same manner, we can do one more operation when we take derivative of second equation, double prime, with respect to x, and combine this with derivative of first equation, just prime, over time. So in that case, we can write that d squared b over dx squared is equal to mu naught times epsilon naught d squared b over dt squared. So we get this in the similar manner when we combine equations which we get after taking derivative of equations 1 prime and double prime. We just do it in different sequence. So now we have our equations, and we can rearrange them in order to make the form similar to the general wave equation. So GBX So we can write eventually the expressions for this general wave equation. It will be d square y over dx square equal to 1 over v second power times d square y over dt square. So this is the general wave equation which you considered in the mechanical, like general mechanics course. And provides dependence of displacement along axis x, along axis y, as a function of position along axis x, along this axis along which the propagation of the wave happening, and time. So if we compare now this general form of wave equation with these two equations which we got for electric field and magnetic field. So for instance, here magnetic field d square b over dx square. So if we substitute now instead of yb, we actually get the same form of as general wave equation like in mechanics, but in this case it will be not about displacement along axis y, but it will be about changing of magnetic field. And the same actually stands also for electric field. So we see we can write down it in shorter form so we don't have intermediate equation. So it will be d square e over dx square is equal to mu naught epsilon naught d square e over dt square. So we see that we can write this relationship between magnetic field and position x and time, as well as electric field position x and time, in the form of general wave equation. So here in general wave equation, we have this term 1 over v squared, where v stands for the speed of wave propagation. So according to this analogy, we should write that mu naught times epsilon naught, which stands before this second partial derivatives of magnetic and electric field over time. It should correspond to 1 over c squared, where c squared is the speed of electromagnetic wave propagation in free space. So if we make this assumption, we can express this speed as 1 over square root over square root of the product mu naught times epsilon naught. So this is the equation which we wanted to get, the expression for magnetic electromagnetic propagation in free space. And now we can calculate it because we know the magnitudes for these constants. These are magnetic and electric permittivity of free space. So we can calculate the speed. Will be 1 over square root 4 pi times 10 to minus 7 Tesla times meter divided by ampere, multiply 8.85 10 to minus 12 Coulomb square Newton meter square, and eventually we will get 2.99792 10 to power of 8 meters per second. So this is speed of electromagnetic wave propagation in free space, and this is precisely speed of light in free space, which was experimentally measured. That's why it's a great combination of experiment research, where you do direct experimental measurements of some parameter and get the ideal match with theoretically predicted value for this parameter. So moreover, it's not just matching of values for a certain parameter. This is, first of all, fundamental constant of physics, speed of light or electromagnetic waves in free space. And also it provides clear evidence that light, this signal which we can observe in the visible spectral range, is just a part of wide spectral range of electromagnetic waves. So it's the same nature as other electromagnetic waves, which we can detect with some antennas or receivers. Yeah.
Well, does that mean that when comparing electron and photon as wave particles, they are essentially the same behavior?
We will definitely discuss these features. So let's say the flux of electrons can behave similar as a wave. That's a concept of like dual concept of the dualism, so-called, because we can consider electrons as particles, and obviously they exhibit features of particles, specifically in some quantum effects like external photo effect, where we also can consider photons as carriers of the quantum of light, and then they can be considered as particles also. However, in other effects like light propagation, like in geometric optics, interference effects, they show that clearly can be described according to the wave theory of light, assuming that it's just electromagnetic wave. So it depends on the conditions of experiment. It is possible for both photon and electron consider as particles or waves. It's just matter of the conditions where we deal with them and which kind of mathematical models we apply, because for some conditions it is much easier to make this assumption of the nature, either particle or wave, and based on that we can perform the calculations and analysis of our either theoretical predictions or experimental results in much simpler and straightforward way. But your question is definitely relevant, and it's true that it's possible to consider from both sides.
Yes, thank you. There have some difference, definitely have difference. Maybe because photons are of negligible weight and electrons have some 10 minus 31 degree weight, and this also affects.
Sure. It's they are described with different statistics. For photons, you use Bose-Einstein statistics. For electrons, Fermi-Dirac distribution statistics. For the population in versus energy. So obviously they are very, very different. However, under certain conditions, they can both either corpuscular, means these particle features, or wave features. And definitely we will discuss this a bit later. Specifically, mostly here we will focus on wave features of electromagnetic waves and light. But during this modern physics course, that will be the time when it's necessary to consider not only electrons but also photons, which are quants of energy which are carried by electromagnetic waves. So that will be highlighted in way more details during this modern physics course for sure.
Thank you.
You're welcome. Yeah, so this is everything what I was planning to discuss with you today. So we considered first and fourth Maxwell equations in order to find the relationship first between time position dependence of electric and magnetic fields with time dependence of magnetic and electric fields respectively. And then by rearranging these equations, we have written them in the form which is the same form of like general form of wave equation, which was in more details derived and explained during our Physics 1 course when we were working with mechanics. So by taking an advantage of the analogy between general wave equation and those equations which we got for electric and magnetic field as functions of position and time, we could determine the quite simple and straightforward equation for speed of electromagnetic wave propagation in free space, which is equal to 1 over square root of the product between magnetic permittivity and electric permittivity of free space. So I would strongly encourage you to remember this equation that is simple and gives you the relationship between 3 fundamental physics constants, which is quite nice. As was figured out experimentally, this theoretically calculated speed of light, electromagnetic wave propagation in free space is equal to speed of light, which can be, at that time it was experimentally measured with relatively high accuracy. It was very close to this value predicted from the system of Maxwell equations. With this, thank you very much for attention and have a good evening. Take care. See you next time.
Thank you. Goodbye.
Goodbye.
Okay, guys. Bye-bye.